So the Towers of Hanoi is a very stereotypical, archetypical, just very famous problem about recursion. Um, it's not just a computer science thing. I actually was watching Big Brother this week, and it was essentially Tower of Hanoi problem was their power of veto challenge. If you've ever watched that show, but it was a little game they made the people play live, where you can only pick up one thing at a time and move it. So let me go through the rules. So the idea is you have three posts, and you have some number of disks or something on those posts, and the rule is that you can only have a smaller disk on top of a larger disk. So it's actually more complicated than what the other problem was. Um, so in order to move the disks around, I have to move it to a post that is legal, something that is open and whatnot. So what you see in front of you here is actually the entire solution to solving that problem. Now, if you've ever seen this game before and tried it, it is non-trivial. There's a pattern to it. You can solve it. It's pretty straightforward. But you would probably not describe the problem in one, two, three, four steps, essentially. The two lines represent the motions you tell somebody to take. This is kind of like the Tower of Hanoi instruction provider. But there's really four steps here so an if statement, and then a call to move something, and then a print something out, and then a call to move something. It's this is ridiculously simple, um, but it's worth going over and understanding this to understand that these things sometimes are just about how you decompose a problem and see what it is. I mean, fundamentally, what I'm saying is, what the heck does these four lines of code mean? So the base case in this case is the trickiest part to sort out. And when I came back and first started thinking about recursion again in the Tower of Hanoi, I really had a hard time figuring out the base case is, because logically you're saying, oh well, the base case is that everything's on the right tower, but the actual base case to defining this, that's traditionally done, is one of the disks is ready to move to a destination. Now, the destination, if you think about what we were just talking about, the destination is this spot over here. And so obviously the destination is to get 5 over here first, and then 4, then 3, then 2, then 1. But if I break down the problem, well, 1 can go to either 1 or 2. 2 then can go to the opposite one. So it's a really simple thing. I'm going to move some disk to some destination, and by defining it that way, then everything else kind of breaks up from there. And so the recursive case is to say, hey, any disks that is on top of the disk that you're trying to move to its destination, get out of the way. And then move the disk to its target destination. And then whatever disks are in the way, move to the support post, that third option inside of there. And the magic of Towers of Hanoi is a flexible definition of the starting point, the support post, and the destination post. So let's walk through a simple example to see how this thing works. So when we start with this, we just have 2 disks on here, and it works for the same command works for 2 disks or 5 disks or 3 disks or whatever number of disks we put out there. We start off with the idea of the bottom disk, disk 2, is going from the starting post to the destination post by way of the support post. That makes sense, right? I can't move 2 straight over because 1's on top of it. So the easy answer to this is I move 1 to the support post, 2 to the destination post, and then 1 on top of the destination. So the logical rules are simple, but breaking it down recursively takes a little bit of a trick. So according to the rules then, in order to get the top one out of the way, number 1 out of the way, I'm swapping what the destination is. So remember, when I'm in the midst of the game, I forget about the bigger picture. So in order to get to the destination post, I have to tell one to go to the support post. But to tell one to go to the support post, I'm setting the destination to be the place I want it to be on the support post, which means if there's other disks on top of it, I need to get those out of the way first and then get that post out there. And that's really the trick of it. That's really the trick is once I've set the rule for one of them, everybody else is conforming down the line from there. So once I've said I want two to get over there, well, now one has to have a new goal, and that's what this new goal is. And so I move one over to its destination, right? And then I'm allowed to move two to its destination. And then I can move one back up from there. And so the bigger problem inside of here is not how do I get five all the way over, but once I've defined where my first step is, if I get five all the way over, how does that translate into the next steps down below? Um, if we come back here and look at the code, break that back. So if the disk number is one, the base case here, the smallest disk, I want to move the disk one from the post it's on to the original starting post, whatever that's going to be defined as the path comes along, and I'm going to return. So that's the last case. That last one goes someplace there. So in the very first call, when I say I want disk 5, number disk, to go from the starting post, this one defined here, to the destination post, this one over here, the last step needs to be, by the way, remind you to bring disk 1 over. But outside of that, I can go through and then switch it up. So if I say disk 5, then disk minus 1, 4 is going to go, instead of the starting post, it's going to go from the starting post, but instead of going to the destination, it's going to go, the destination and the support are swapped. I'm going to move that disk right there, and then from there, I'm going to undo that move. So disk number 4 goes from the support post to the destination post. So 5 goes to, in order for 5 to go all the way over here, I need 4 to go over here, and then 4 to move over to there on top of it, right? And so in order to make 4 go over to here, I need 3 to go over to here. But in order to make 3 to go over here, I need 2 to go over here. But in order to make 2 to go over here, I need 1 to go over there. And so that's where you can kind of get this judgment back and forth. You're just hopping back and forth and whatnot. So it's a really cool algorithm. It's really hard to show without making 1,000 slides of how that moves. But I wanted you to get a feel for it because recursion can be tricky. And seeing an example of what's supposed to happen and the logic of what's supposed to happen can really make it easier to do it along the way. And the more you practice, the better you're going to get at this. So again, the idea is to find the base case, find the recursive algorithm, and then move along each bit of the way. But part of the trick as well is visualizing it. And what I mean by visualizing it is finding some ways of expressing the data. In the code I showed you there, I use a print line to make it happen. I wasn't going to do an animation and create a whole GUI. And that could be a trick as well. So from here, there's a whole list of recursive problems. If something looks ridiculously easy, then do it. Knock it out. Prove that it's easy. If the next problem looks exactly the same as that one, then skip it. You can always come back to it. But find something else that looks very doable, you think you know how to do it, and then prove it. And then just keep working on the problems. I mean, if you really want to be a great computer scientist, try every single one of the problems that is out there. You don't have to do them all before you get your grade, but try them all. And anything you get stuck on, submit it. We'll talk about it. We'll figure it out. We'll work on it from there. The biggest thing about here is since recursion is a somewhat limited space, you can Google and find the solution to almost any one of these things pretty straightforward. That doesn't necessarily constitute cheating, so long as you build, test, and understand the code on your own in the end. It's not a matter of whether you can churn in all these problems. I don't care if you turn them in all. I don't care if you turn in none of them correct, so long as we have a back and forth and we get you closer and closer. I'd like you to get a few of them right. Um, Eventually, back and forth. But certainly, I don't care about you turn them in correct the first time right away. I would what have happened is if you get sat down in an interview and somebody says, "How do you solve this problem? Show me a recursive algorithm to do it." I want you to be able to do it. I want you to be able to impress somebody. So again, don't worry about the answer. Don't worry about the code being right. Don't worry about finding the right code. Worry about building the right code with your own two hands over time. About finding out where your thinking needs to conform to this. It's always easy to solve a problem, not easy, but it's always more accomplished when somebody has an algorithm that works perfectly, just to figure out a way to code it. That's not all that bad. It can sometimes be tricky, but learning to construct the algorithm, especially when you only have vague hints at it, is a really powerful skill. That's where you really start to get paid well and become valuable and be able to tackle problems you never thought you could. And that's not all about pay. Sometimes it's about the challenge of stuff. Sometimes it's about finding ways to help people and solve new problems that's never been solved before. Um, so all, think about that as you move forward, and we're going to continue to practice these things as we go forward and go from there. All right, so best of luck. Let me know how I can help. There might be more of these videos that show up beyond this one, but for now, this is going to be the end of the sequence.